Welcome to the Introduction to FPGA AI Suite online training. In this training, we will start with what is artificial intelligence, followed by why FPGAs are good for AI, OpenVINO and FPGA AI Suite development flow, FPGA AI Suite compilation flow, AI Suite IP creation flow, steps involved in the tool flow, and finally, we will explore FPGA AI Suite reference design examples. In this section of the training, we will learn about artificial intelligence, machine learning, and deep learning. Artificial intelligence, or AI, is a broad field that has existed for decades and encompasses any technique that computers use to mimic human intelligence. AI has evolved over the decades to use newer and better algorithms, and nowadays, much of AI is driven by deep learning. Machine learning is a subset of AI that focuses on using algorithms and models to enable machines to learn from data and improve their performance over time without being explicitly programmed. Deep learning, or deep neural networks, is a subset of machine learning in which a deep layered neural network learns from large amounts of data. Deep learning algorithms are neural networks with many layers. The FPGA AI Suite currently solves the space of convolutional neural networks and multi-layer perceptron models. Deep learning models are trained using large amounts of data and algorithms that are able to learn and improve over time, becoming more accurate as they process more data. This makes them well suited to complex, real-world problems and enables them to learn and adapt to new situations. Deep learning can solve multiple supervised and unsupervised problems. The majority of its success has been when working with images, natural language, and audio data. Examples are image classification and detection, semantic segmentation, natural language object retrieval, speech recognition, and language translation. A deep learning graph defines the structure of the arithmetic that the AI model is going to perform on its inputs. The computations in the graph are structured in layers, where every layer just produces some hidden intermediate result, and then the final layer of the graph produces the output of your AI model. The graph contains a huge number of tunable numerical parameters, which are called the model weights and training. When the training is complete, we take the graph and the model weights together to form a trained AI model, which is to be deployed into the product. When the trained AI model is actually running in the product, doing whatever task it was trained to do is called as computation inference, and this inference happens in the FPGA device. In this section of the training, we can understand why FPGAs are good for AI applications. The comparisons between GPU versus FPGA for AI applications are shown in the table. FPGAs are good for optimized, low-power, low-cost AI solutions for specific needs. FPGAs are a great fit where power efficiency, TCO savings, real-time processing, deterministic low latency, and tighter integration are the keys. FPGA support for multiple I/O standards, which is ideal for fusing and merging different sensor and camera types. FPGAs have longer product life cycles compared to GPUs. FPGA systems naturally enable AI. FPGAs, with their thousands of DSP blocks for compute, offer programmable data path. FPGAs, with their variety of memory hierarchies, offer customizable memory structures. Existing FPGA users who are looking to add AI to solve system-level challenges could take their existing designs and simply add AI inside the FPGA. There is no need to introduce new silicon architectures like GPUs. FPGAs are lower power with smaller form factors than GPUs and will give you great TCO and fast time-to-market benefits. The other key value proposition is addressing the constantly evolving AI trends. FPGAs offer flexibility and programmability to customize your design and build the AI network from ground up to get best performance. Altera Agilix FPGAs provide tight coupling of programmable logic with DSP blocks to easily add AI to your custom solutions. The Agilix 5 FPGAs, the first FPGA with fabric infused with AI tensor blocks, is for increased compute density. It enables low, deterministic latency and real-time processing for models deployed at embedded or edge. For data center deployment, we have Agilix M-series FPGAs with HBM2 memory, DDR5 or DDR4 support, well suited to solve memory-bound AI bottlenecks for generative AI LLM-based transformer models. FPGA AI Suite provides push-button conversion of your pre-trained model to AI inference accelerator IP. As your AI needs start to evolve, Consider adding AI to your designs in the FPGA, thus helping reduce development costs and fast time to market. FPGA AI Suite is the fastest, quickest way to convert AI model to AI accelerator IP and deploy them on Altera FPGAs with optimal latency and performance. You can build a custom fabric accelerator using a traditional RTL approach, which gives you least latency, or use a high-level synthesis design entry method like SYCL HLS or DSP Builder. If your AI model is very small, like TinyML, you could run them on the ARM core or even on a Neos 5 processor and accelerate the IP with custom instructions. The details are depicted in the slide for your reference. Altera broadly categorizes FPGA AI use cases as edge AI use cases that could be developed using FPGA AI Suite and OpenVINO Toolkit. Custom AI accelerator developed using traditional FPGA flows, like any other traditional FPGA design, like Gen AI LLM models. AI attach use cases where FPGAs assist with AI processing on GPUs. In both Edge AI and Gen AI or custom use cases, Altera FPGAs offer versatile and efficient solutions for accelerating AI tasks, particularly in applications where customization, deterministic, low latency, tight integration, and energy efficiency are critical. In this section of the training, we will get introduced to OpenVINO and FPGA AI Suite development flow. Let us first explore the AI team profiles and their roles before diving into the FPGA AI Suite. The FPGA engineer's goal here is to get the AI inference IP integrated with the rest of your FPGA design using Platform Designer and close timing in Cordis. There could be a software integrator who integrates the AI inference IP to the host processor. Bridging this gap between the world of the data scientist and the world of the FPGA designer is not an easy thing, and this is especially true if there are going to be multiple iterations where we might have to go back and refine the AI model based on the findings of FPGA design and deployment. So, this is exactly the problem that the FPGA AI Suite is designed to solve. To use the FPGA AI Suite, first convert your trained model into the OpenVINO intermediate representation known as IR model. Start in the data science world. Data scientists use a machine learning framework to train the AI model. OpenVINO stands for Open Visual Inference Neural Network Optimization. OpenVINO is an open-source toolkit developed by Intel for deploying deep learning models. OpenVINO Model Optimizer is a command-line tool that takes in a trained deep model from almost any framework and provides OpenVINO IR model as the output. Advantage of OpenVINO toolkit is its ease of use, since it handles all popular ML frameworks as input and provides common IR as output. The high-level definition of the FPGA AI Suite can be stated as follows. FPGA AI Suite provides complete solution to rapidly convert an optimized, trained AI model to custom AI inference accelerator and deploy on Altera FPGAs, enabling seamless collaboration between data scientists and FPGA engineers with easy-to-use tools. Let us understand now how FPGA AI Suite works. You can import your pre-trained model from any standard frameworks like TensorFlow, PyTorch, etc. into OpenVINO Toolkit's Model Optimizer, which converts the model into an intermediate representation. FPGA AI Suite tool takes IR data as input and generates AI inference IP that can be integrated into the FPGA design using standard Cordis flows and generate bitstream. AI Suite gives you resource usage upfront, comes up with optimal FPGA architecture for your performance needs. The software flow takes the intermediate files from OpenVINO, runs it through the OpenVINO Toolkit inference engine to generate the runtime that can be run on x86 or ARM or RISC-V processor. The benefits of the FPGA AI Suite are shown in the slide. Support popular AI frameworks. The front end of the FPGA AI Suite is the OpenVINO Toolkit. The toolkit seamlessly converts pre-trained AI models from most standard frameworks to intermediate representations that FPGA AI Suite uses. Access to free pre-trained AI models. Support for most of the deep learning models on OpenModel Zoo for OpenVINO Toolkit. Jumpstart your solution development by picking the best suited model. Ease of use. Rapid development using software. Easy integration of AI inference IP. Add AI inference IP to FPGA design with standard Cordis Prime FPGA flows. Integrate IP with other system-level components to achieve a small footprint and lower power, latency, and system costs. This section explains the details of the FPGA AI Suite compilation flow. The steps involved in the software implementation flow are: Step 1, build and train AI model with popular frameworks. Step 2, use OpenVINO model optimizer and convert into IR model. Step 3, run quick performance and area estimates to check whether the model meets target metrics. Step 4, run software emulation to check the accuracy of the FPGA AI suite IP. Step 5, auto-optimize the IP architecture for given area and performance target. Let us focus more on the FPGA AI suite graph compiler. The FPGA AI Suite compiler generates optimized FPGA AI Suite architecture configurations suitable for executing a given set of OpenVINO graphs within specified system constraints. It estimates the performance of an OpenVINO graph on a given FPGA AI Suite architecture. It estimates the FPGA resource requirements for a given parameterization of the IP. It produces compiled binaries of OpenVINO graphs suitable for execution on a given FPGA AI Suite architecture. The FPGA AI Suite compiler, the DLA_compiler command, is built on the OpenVINO framework. Use the FPGA AI Suite compiler, that is DLA compiler command, to do the following tasks. Compile the IR of your graph to an FPGA bitstream. Estimate the performance of a graph. Estimate the performance of a partition of a graph. Estimate the FPGA area required by an architecture. Generate an optimized architecture. Generate an optimized architecture for a frame rate target value. The DLA_compiler command format for compiling a graph is shown for YOLO model targeting Agilex 5 device. Use the DLA compiler fanalyze area command to check that the FPGA AI Suite installation was successful. Once installed successfully, this DLA compiler command will run the area estimator. The .arc file specifies one or more FPGA AI Suite architecture files to use in the flow. Fanalyze area option allows the compiler to estimate the area of the specified architecture. March sets the path while compiling graph. Use the fanalyze performance DLA compiler command option to estimate a graph's performance on an architecture. The DLA compiler command compiles the graph for the specified architecture to estimate its performance. To generate an architecture optimized for a graph, the FPGA AI Suite Architecture Optimizer uses a base architecture and modifies parameters to achieve the highest throughput in frames per second, known as FPS. The best architecture is saved as an architecture description file with a file name based on the architecture parameters. The example command to generate the highest performance is shown in the slide. The AI Suite IP has a highly configurable architecture. Configuring the design allows for different trade-offs between inference performance and utilization of FPGA resources. Configurations are specified through architecture description files. Some of the configurable parameters are listed in the slide. The architecture optimizer helps sweep the design space for the best performance for a given FPGA area target, that is, logic elements, memory, and DSP blocks, or a smaller FPGA area for a given target performance, frames per second or FPS, and gives you an architecture file with the best possible parameters for your graph. However, some parameters like enabling or disabling activation functions, architecture precision parameter, need to be done manually and explicitly. The architecture optimization process uses the compiler, the performance estimator, and the area estimator. To generate the smallest possible architecture with a minimum target frame rate, FPS performance constraint, use the mTarget FPS option in addition to the options used to generate an optimized architecture. If you specify both the mTarget FPS and max resources options, the optimizer tries to satisfy both constraints. The output files are the same as when generating a performance optimized architecture. Optimize the architecture for the highest performance subject to a constraint on the maximum allowable FPGA area, or optimize the architecture for the smallest possible FPGA area subject to a constraint on the minimum target frame rate. This slide shows the important reports generated by the FPGA AI Suite. The Architecture Analyzer report aids in optimization of FPGA resources. The per latency report displays latency information for each layer and subgraph. The Model Analyzer report provides detailed information about the model layers. The unsupported layer chain graph visually aid debug of model compilation. We will understand more on Model Analyzer report and unsupported layer chain graph. The Model Analyzer report will display the relation between layers in the original OpenVINO graph and the ones in the transformed OpenVINO graph. Multiple layers in the original graph might be fused, others might be split, while some might be changed entirely. The model analysis report contains information about the model, the layer placement information, the reason why layers were unsupported, and how internal layers relate to the layers from the original OpenVINO graph passed to the FPGA AI Suite compiler. The report generated will be similar, like as shown in the slide, which has true and false indications. The unsupported layer chains report contains a visual representation of the unsupported layers of the model. The report is structured to highlight nodes as follows. Nodes that are directly unsupported by the FPGA AI Suite compiler are highlighted in red. Nodes that are unsupported due to other nodes being unsupported are highlighted in orange. Nodes from the original model that have been unsupported are highlighted in blue. Trace from any unsupported node in the original graph to find the root causes of lack of support. In this section of the training, we can learn about the IP creation flow. Here's the FPGA AI Inference IP implementation. FPGA AI Suite IP is a very highly parameterizable IP. The architecture description file describes the parameterization in a human-readable text format, and we use the FPGA AI Suite IP generator to take that .arch file and generate an IP in Platform Designer format that you can use to integrate into your rest of the FPGA design. The FPGA AI Suite IP integration flow is listed in the slide. Step 1. Generate FPGA AI Suite IP. Step 2. Integrate FPGA AI Suite IP in Platform Designer in Quartus with other IPs, close timing and generate bitstream. Step 3. Program bitstream onto FPGA. The FPGA AI Suite IP generation utility reads an input architecture description file, .arch, and places generated IP into an IP library that can be imported into Platform Designer or used directly in a pure RTL design. The IP generation utility generates either an unlicensed or a licensed copy of the IP. The unlicensed IP has a limit of 10,000 inferences. The IP generation utility has the following flows: creating an IP directory, adding an architecture to an IP directory, listing architectures in an IP directory, removing an architecture from an IP directory. The simplest DLA create IP is shown in the slide. Use the architecture option to specify one or more architecture description files. Use the architecture directory option to specify a directory that contains one or more architecture description files. All architecture description files in the directory are added to the IP library. Use the IP directory option to specify the output FPGA AI Suite IP library directory. If unspecified, the default value of AI Suite root directory is used as the IP library directory. You can specify the overwrite option to overwrite the IP directory and create a new IP if the IP directory already exists. If the overwrite option is not set, the script prompts you if want to overwrite the IP library directory. The default structure of the FPGA AI Suite IP directory is shown in the slide. The intel.ipx will be used by the Platform Designer to recognize the IP. This section provides the overview of the tool flow. The steps involved in the flow are: use the DLA compiler command to check that the FPGA AI Suite installation was successful. Creating a working directory, preparing Open Model Zoo, preparing a model, download the ResNet 50 TensorFlow model and run Model Optimizer, running the graph compiler, FPGA AI Suite architecture generation flow, FPGA AI Suite IP creation flow, integrating the IP with Quartus Prime design software. Use the DLA compiler fanalyze area command to check that the FPGA AI Suite installation was successful. Once installed successfully, this DLA compiler command will run the area estimator. The .arch file specifies one or more FPGA AI Suite architecture files to use in the flow. fanalyze area option allows the compiler to estimate the area of the specified architecture. March sets the path while compiling graph. Create a working directory for the FPGA AI Suite design files and copy the files into the working directories. Download a copy of Open Model Zoo and run the commands as shown in the slide. A model must be converted from a framework into a pair of .bin and .xml files before the FPGA AI Suite compiler can ingest the model. The OMZ downloader command downloads the trained model. The OMZ converter command runs Model Optimizer that converts the trained model into intermediate representation.bin and .xml files. The FPGA AI Suite Compiler (DLA) compiler tool can estimate the performance of a graph and IP architecture combination. The tool can also produce a compiled network that the runtime uses an AOT or ahead-of-time mode to control inference on the IP. The command explains the architecture file, which specifies the configuration of the IP architecture configuration parameters, such as large, small, and which activations to use. The .xml file along with the .bin describes the network. The .bin file stores certain parameters along with the model weights and the mapping files. To generate an architecture that is optimized for a graph, the FPGA AI Suite Architecture Optimizer uses a base architecture and modifies parameters to achieve the highest throughput in frames per second. The best architecture is saved as an architecture description file with a file name based on the architecture parameters. The DLA create IP command is shown in the slide. The intel.ipx file, which is used by the platform designer, is shown in the red box. Open Quartus Prime Design software and navigate to the Tools menu at the top. Then select Options to add the newly created IP to the IP catalog. Select the button with 3 dots and navigate to the folder containing the IP you created. Now you can see the IP in the IP catalog on the right side of the Quartus software. Double-click on the IP to launch Platform Designer to add to your Quartus Prime project. Complete the system and ensure that there are no errors. The hard processor system and the IP integrated to the design are shown as red boxes. Let us discuss now on the software emulation model of the FPGA AI Suite. Software emulation of FPGA AI Suite IP is bit accurate. Emulation of the FPGA AI Suite IP is accessible through the OpenVINO plugin interface. Enables quicker evaluation of accuracy of the FPGA AI Suite IP without access to hardware. Inference using the software model is much slower than on the FPGA, but using a compute farm can perform enough inferences to validate the model. Model is accessible through the OpenVINO plugin interface. Activation functions are critical in how neural networks operate, deciding how the system responds to new data and learns from it. The FPGA AI Suite now supports the following activation layers: 10H, sigmoid, swish, and reciprocal. These layers were previously executed on the CPU. This support will give developers more flexibility when building AI models, making them more efficient and better suited for different tasks. In this section of the training, we will explore the reference design examples available with the FPGA AI Suite. PCI Express-based design examples for Agilex 7 devices based on Thoracic. FPGA AI Suite SoC design example for Aria 10 and Agilex 7 devices. New hostless DDR-free design example for Agilex 7i series development kit. Axis streaming support and DDR-free inference reference design example based on Agilex 7i series development kit is shown in the slide, which is targeted for low-cost and low-power inference designs. Follow these 3 quick start steps to perform the SoC reference design example. First step is to start with pre-built inference test with basic video frame. Second step is to try out inference from Linux command line from PC. Third step is to look at the results. The example design can be run on different boards: Aria 10, Agilex, and Stratix 10 FPGA. There are 2 modes for this reference example. A simpler one called memory-to-memory mode M2M, and a second one in the next slide called streaming-to-memory S2M. Here is the simple data flow for M2M. First step is where hard processor system writes to external memory interface. Second step is the IP core inference. Third step is the HPS readback. The steps involved here are: first, HPS writes to fabric-based layout transform. Second step is where transformed image gets written to external memory interface. Third step is the IP inference. Fourth step is the HPS reads from external memory interface. Customer receives full source code for the software stack. It includes Yocto Linux host running on the ARM SoC, OpenVINO inference engine, and API compiled for ARM, including OpenVINO ARM community plugin at the link provided here. Software stack allows fallback from FPGA plugin to ARM plugin for layers that are not supported by the FPGA plugin. Full FPGA AI Suite OpenVINO plugin plus runtime. For S2M only, VIP Linux framebuffer to create the streaming data. Customers can start with example design, expand and build their AI inference application with Quartus. The figure shows a typical hierarchy with the inference IP, ARM, and memory subsystems. The timing constraints are the vertical green box. A simplified flow is described in 3 steps. First step is to load new custom network into Quartus project and rebuild design. Second step is to include new datasets onto SDHC card. Third step is to run dataset with included application and collect results. Refer to the latest release notes and Getting Started Guide for the latest information. Release notes, Getting Started Guide, IP Reference Manual, Compiler Reference Manual, PCIe-based Design Example User Guide, YesOC-based Design Example User Guide, Agilix 7 AI Design Guided Journey. To target Agilix 5 device, change AGX 7 to AGX 5. Note, Agilix 7 does not include enhanced DSP with AI TensorBlock. The FPGA AI suite enables FPGA designers, machine learning engineers, and software developers to create optimized FPGA AI platforms efficiently. Utilities in the FPGA AI suite speed up FPGA development for AI inference using familiar and popular industry frameworks such as TensorFlow, PyTorch, and the OpenVINO toolkit, while also leveraging robust and proven FPGA development flows with the Quartus Prime design software. FPGA AI Suite generates right-sized AI for your latency, power, and performance needs. Thank you.